Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Igor Volkov and Alexandra Kravtsova with us today. Hello, Sasha, and hello, Igor.
Hello.
Hello, Frank.
Go ahead.
We are here in Moscow.
Oh, in Moscow. Okay, very cool. So I'm here in Phoenix. So we're separated by a good half of the world here. Is it snowing yet in Moscow?
Yes, it is. It's -10 now.
Okay. How much snow does Moscow get? Does it get like a meter of snow, several meters of snow?
15 centimeters.
Centimeters. Okay, a tenth of a meter. Okay, very cool. All right. We don't get that in Phoenix. We don't see that kind of snow in Phoenix. We're more in the desert. So. Very cool. Igor and Sasha, what do you like to do for research? And we'll start with Sasha. What do you like to do for research, Sasha?
Excuse me.
What do you like to research?
What do you like to do for research?
Research?
Excuse me.
What kind of astronomy do you like to do? What kind of astronomy do you like to do?
I study. Sometimes I make observations on telescopes. Sometimes I make some calculations. Sometimes I process our observations.
Very nice. Very nice. And Igor, what do you like to do?
No, I have a long-term program of observations. This program was started by Professor Martinov early in 20th century with a very interesting star of RU Monocerotis, which he has observed photographically.
Yes.
He has found with great eccentricity, and so is our interest, or the interest of researchers in our institute in such investigations of eclipsing stars, which have a very high eccentricity.
Yes.
This program was continued by Professor Khaliulin. He was the student of Professor Martinov.
Oh, okay.
And in next turn was my turn, and I am the not student, but he is my supervisor. Professor. He was a supervisor of my PhD thesis. And so I continue this work in our institute, in Sternberg Institute of Moscow, Lomonosov University.
Very cool. Very cool.
Yes.
I'm honored. I'm honored. And that is going to bring us to this very awesome AJ article. It's open access, people. You can go get it for free. Go get a copy. And Apsidal motion and physical parameters in the eclipsing system V90 SCT. And Igor and Sasha, take us away.
Okay. I want to say some words about this system. This system was found nearly a century ago, also by a photographic method. It was investigated by I don't know, doctor. No, he wasn't a doctor. Otterdijk on the plates which were obtained in south constellation of Sagittarius.
Yes.
And he has found very precise for this not very precise method. He found that eccentricity was 0.4, and we were not able to get more precise value. Our value is 0.4. 0.4 also.
Okay. Okay.
Yes.
Mm-hmm.
This system was neglected by other researchers. I don't know the reasons. Maybe to the fact that firstly it was found to be in Sagittarius constellation, but really it is situated in Scutum constellation. So Professor Samus has changed the designation of the star. So in some catalogs, it was named as V1049 Sagittarius, and in more in next catalogs it was named as V490 Scutum.
Huh. I did not know that. Okay.
It's situated only 8 minutes from the bound of the between these constellations. So, so I have started the observations a very long ago, but I wasn't lucky to find any minimums of the star. Till 15 years ago or 17 years ago, occasionally I found one of the minima, and after this we have a checkpoint and we have started the continuous observations of the star in different observatories with different instruments.
Cool.
The star is of 13 magnitude, so we haven't opportunity to get spectra of the star. So we made only UBV or UBVI photometry.
Okay.
U observations are especially difficult because this star is the interstellar absorption is very strong in the direction of the star. So the signal in U is very low.
Yes.
So we have got not a lot of observations in this filter, but they are very important because they made it possible to find the temperature of the components. And it is a very important parameter. If you have no spectra, this parameter is very important to make the estimations of the masses of the stars. So having so we obtain in figure 1 you can see the color indices of the light loss in minima. This method I have found in the paper of Professor Popper, where he has investigated DI Hercules. And this method is very convenient to find the color indices of each of the component.
Great.
Because the color of light loss is not contaminated by the light of other component or third component if it exists in the system. So in this picture, we can see that V minus R for the component which is eclipsed in secondary minimum is less than for the component which is eclipsed in more deeper primary minimum. So the situation in the system is inversed. In a more deeper minimum, not so the component with not so high temperature is eclipsed. It is due to the it can be explained only by orientation of orbital ellipse. because the parts of eclipsed parts of the discus are different.
Yes.
So it's not very convenient to explain.
I got you. I'm with you. I'm with
Because the primary component, normally the primary component belongs to primary minimum. Here, the primary component belongs to secondary minimum. So component A is eclipsed in secondary minimum.
There you go.
Shallow minimum.
Mhm.
No, but doesn't matter. It's
Mhm.
only a question of naming of this stuff.
Yes.
So
Mhm.
the multicolor photometry allowed us to find the lower place text.
Yes, please. Okay.
Yes. Allowed us to derive the interstellar absorption.
Yes.
In figure 2, we see the U minus B and B minus V diagram. The line belongs to the mean position of the star according to Strasser's calibration. Here is citation of Strasser's. And to show the reliability of this calibration, we put this UBV magnitudes of the stars from Mermillion catalog on this plot.
Yes.
So crosses are the observed positions of the star. We see that the condition of equal interstellar absorption for both components can be fulfilled only for the area close to AO spectra, not for A7.
Right. Right.
Though the line of interstellar absorption crosses the normal line in two positions, in two places. It's very important because the temperatures and masses of the stars in these 2 points differ a lot. And the Gaia parallaxes satisfy the position close to B9 and AO for components satisfies better for the parallaxes, for Gaia parallaxes.
Yeah, okay.
So higher temperatures needed for the stars. So we have made estimations of masses. From masses, we obtained the estimations of probable Apsidal motion, or the rate of Apsidal motion, and found that the observed value, which we found from our 17 years observations, a little bit slower than it follows from theory. So this star stays in line with such stars as DI Hercules or AAS Camelopardalis, which demonstrate lower Apsidal motion. And
good.
It's interesting to say that after the referee correction, after referee
helped improve paper
notes, after referee's notes, we have undertook the special observation of AS Camelopardalis and have found the explanation of slow Apsidal motion in this system also.
Okay.
So the referee notes force us to undertake a special investigation.
Okay.
Which continues nearly half a year. So it was the process of publication was lowered.
Right.
Yes.
Okay.
No, what to add. No, we can go to other pictures.
Okay.
Some words on. No, in table 4, we publish the characteristics of the stars, the individual. Our individual yes, here, radii, acceleration, gravitation on the surface of the stars,
Acceleration.
photometric parallax, photometrically determined distance, yes, which is close to Gaia parallax.
Okay.
No,
Okay.
the distance, yes. Next picture we can.
Next one. Okay.
Next pictures.
Okay.
Here you can see that there are not a lot of observations in U, but they are very important. So
Yes.
here are observations in minima, in secondary minimum. No, in primary minimum are the same picture, and under the picture we see the residuals from solutions. From obtained solutions in different filters, in different photometrical bands.
Okay.
Yes. Lower the plot is the plot. A little bit lower. Figure 5.
Figure 5.
Yes. Normally, for such a class of stars, the dependence of residuals from yes, here, from radii ratio is the bottom of residual is flat. So it's very hard task to find the real ratio.
Yes, I'm with you.
Of radii. So to make this plot more contrast, next plot, please.
Yes.
We used our indirect method of determinations of parameters of the stars and compared the lower.
Okay, I'm with you.
Yes, here, this parabola-like plot.
Yes.
And compared the distances of the components which we can obtain for different radio ratio, and found that more pronounced minima is nearly equal radii of the stars, but the more hot component should be a little bit bigger.
That's a big K.
It follows from evolutionary. Yes, method which suggests Professor Popper, higher figure 6, please.
Yes, this one.
He suggested to compare the residuals obtained for different radii ratio and simply to look on the plot and find some systematic in these pictures and find and to take the ratio with less systematic in residuals. But for these stars, we have found all of these plots look equal.
Yeah.
So this method doesn't work.
Right.
Maybe to the much lower inclination of which we found in the star, 88 degrees, not 89, not nearly equal to 90 degrees as for the Ig Hercules. So let's go to other pictures.
Sure. Figure 8, figure 9.
No. When we have found the parameters, we compared them with the evolutionary tracks from Girardi models and found that the components satisfy them quite well for solar chemical abundance.
Okay.
In table 6, we put all individual timings which we found for the star, and can say that there are no other measurements in literature.
All right.
So no other investigation of this star.
Very nice. Very cool. Yeah.
And lower for.
Wow, yes. Yes, very good.
But this table
very good.
enables us to find the
Nice.
rate of apsidal motion in the system with high accuracy.
Okay.
Though the period of the apsidal rotation is close to 40,000 years, we have found it with the precision of, we think, better than 10%.
Nice. Very good.
Yes. Yes. And some words about apsidal motion, maybe.
Yeah.
To resolve the discrepancy between theory and observation in the system, no, a little bit lower. We found a little bit lower apsidal motion of the system. We calculated the theoretical rate of apsidal motion for different inclinations of the components, and have found that if the components are tilted a little bit to the plane, to the orbital plane, the rate of apsidal motion can be explained by this effect, by the tilt. Okay. No other suggestions should be needed to explain. No, but for in future, it's be very useful to obtain spectra of the star, but we haven't such instrumentation in our disposal. Okay. Maybe Smith telescope can help, but this star is has a very south declination in our for our country. So maybe in Chile it's better to observe.
Helps be in the southern hemisphere, yes.
So, I think we should continue the observation, but it's only one of the stars of our list, which contains more than 100 objects. So we were lucky to that Astronomical Journal was in interest to publish this investigation. Oh, very long investigation.
Yes, this thing has quite a timeline to it. It's very nice, very nice. And Igor and Sasha, I want to thank you once again for walking us through your very lovely Astronomical Journal article. Thank you.
We plan to publish 2 more articles.
Okay. Yes.
Yes.
On the same system or on different systems?
No, on other systems.
Okay.
On other systems. Some of them is Alpha Corona. It's the second eclipse, the second brightness in eclipsing stars. This only one star is more. Only one eclipsing star is more bright than Alpha Corona Borealis.
100 of them. So.
And it's very difficult to observe because the secondary minimum is only 2% deep.
Okay.
And the magnitude 2.2 magnitude of the star. And I have found some opportunities, some method to observe this star with high precision. I used different methods. I think maybe it will be interesting for your journal.
Nice, very cool. I look forward to seeing those manuscripts.
Yeah.
So I look forward to seeing them. Very good. Igor and Sasha, I want to thank you very much for walking us through your very lovely article. And that'll do, everyone. And we'll see you on the next one. I hope this made your astronomy day just a little bit better. Bye-bye.
Thank you very much. Bye-bye.